Okay, I'm going to work through an example where I am finding the volume of a solid region that's formed by revolving a curve or some curves around one of my axes. I'm actually going to do this one two different ways, so follow along. This is example 12 if you're in your packet, and I'm going to be revolving this around the y-axis according to instructions. So let's go ahead and sketch a curve in here. I've got 4 minus x squared, which I'm recognizing as a parabola that opens down and is shifted up 4 units. So that looks something like this. Again, I'm just doing this by hand. So that's a rough sketch of my parabola. And then I've got the line y equals x, which is going diagonal through my graph. So those are going to intersect at some point. I'm not exactly sure what that point's going to be. So I'm going to go ahead and get rid of the extras here, and then of course draw the rotation because I'm going about my y-axis. So we're ending up with something like this that's rotating around, and I guess I'll kind of draw that rotation happening, I don't know, sort of like an awkward top, right? It's spinning on a point, and then it's got this dome shape on the top. And then the line x equals 0 was my other, that's my y-axis, so that was my other boundary. So this is my initial curve, and then I'm rotating it around. I'll go ahead and highlight that in blue so you can see the initial curve was the line x equals 0, the line y equals x, and then the parabola y equals 4 minus x squared. So I've rotated that around, and I want to find the volume. Okay, my first thought is let's go ahead and slice that. And can I slice it? It doesn't look like I'm going to have to do washer method because there's no hole in the middle. It's not hollowed out. It's going to be an actual solid. So can I slice that horizontally? And if I slice that horizontally, that's going to look like this, taking out a disc or a very thin cylinder of really tiny thickness. It's going to look something like this. My thickness, of course, is with respect to my y-axis, so I'm going to call that dy, that little tiny thickness. And I'm going to say if I find the area of one of those discs and I add them all up, then I can, using an integral, then I can actually calculate the volume. So volume is going to be the integral. I'm going to put my pi out front, and then I need my radius squared. And for the part that I just drew, my radius is really my x value. But because I'm integrating with respect to y, and I'm going to have a dy here, my x value, and the reason I'm saying x, if you take a look at your picture, I'm saying x because I'm looking at my radius as the distance from the center out. That's really my x value on my graph. I need my x, but I need to solve for it in terms of y so that it matches my dy here. So I'm going to take a second and go ahead and do that. If my y equals 4 minus x squared, to solve for x, and I could go ahead and switch my x and my y. Let's say, let's add x squared. So positive x squared is equal to 4 minus y. And then let's go ahead and take the square root of both sides. So I'm going to get y equals the square root of 4 minus y. And then I've got this other equation too, so that's one of them. And then I've got, sorry, x equals the square root of 4 minus y. Then I've got y equals x, and of course if I solve for x, x equals y. So in my first section that I have, the top section, I'm going to be using the curve is actually my parabola. So I'm going to be using this one, the x squared, or the x equals square root of 4 minus y. So I'm going to go ahead and put that in. Remember, that's my radius, but I need to square it because my formula says pi times radius squared gives me area. So I'm going to square that. And I have a slight problem here, and that problem is that I'm only integrating, for that one, slicing my discs horizontally, I'm going to have a radius of 4 minus y, square root of 4 minus y, until I get to this point down here. And then after this, my radius actually changes. If we do a disc at the bottom, let me go ahead and use a different color. So we'll go ahead and use a purple down here. And if you notice, I can take a slice out here, but now my radius is not actually defined by the curve square root of 4 minus y, or 4 minus x squared. My radius is actually defined by the distance from the center out to my line y equals x. So I'm going to have to actually set up two integrals if you follow where I'm going with this. And the first one I've got set up. The second one is going to be integral of y dy, where that y squared, because my formula says radius squared, y is my line, y equals x or x equals y. Okay, and therefore my radius right here. So I've got that set up pretty well. I'm forgetting my limits of integration. So I'm definitely going to be starting, for my limits of integration, I'm definitely going to be starting at 0 over here. And I'm going to be going to some point, and then I'm going to be starting at that point here and going up to 4. I do know that I end at 4 because that is my y-intercept of my parabola. So I know that's going to be a 4. The question is, what's my unknown number right here and right here? So I'm going to take a quick minute and solve for that. That's really the intersection point between my two graphs, my parabola and my linear function. So I'm going to do a quick little aside over here and solve for that. I need to know when does 4 minus x squared actually equal x, which is really when 0 is equal to x squared plus x minus 4. And I'm going to try to factor that. That's not going to factor, so I'm actually going to have to go to use my quadratic formula, or we could be graphing the parabola and the line and finding the point of intersection. And you should be getting a value of 1.562. Let's go ahead and round that to 3 decimal places. So 1.562 is the number that I'm going to put, in, get rid of that, for my upper and lower limit of integration respectively. 1.562 is going in here, and then 1.562 is going in here. Okay, now remember, those are y values. Well, they're x values and y values. Because that's my line y equals x, it's the same exact value. So it doesn't matter which one you do. Okay? So from there, let's go ahead and evaluate this integral. So give myself a little bit more room here. And now it's just the nitty-gritty. Let's do the calculus part. So pi times the integral of, let's tidy this up, 1.562 to 4 of 4 minus y dy. I can go ahead and get rid of my square root and square, cancel each other out. So 4 minus y dy plus integral, oops, I meant to write the pi out front. Pi times the integral from 0 to 1.562 of y squared. I do need to keep the squared this time, y squared dy. Not looking too bad. So I'm going to have 4y minus y squared over 2. Evaluate that from 1.562 to 4. Multiplied by pi at the end, plus pi times the integral of y cubed over 3. I'm sorry, not the integral. I evaluated the integral. I've got the antiderivative y cubed over 3, and I'm evaluating that from 0 to 1.562. At this point, we've got decimals. You probably want to grab your calculator. So grab your calculator, see if you can compare, and take a minute, pause the video, see what you can get. I'm going to say that on the left-hand side, I'm getting an answer of 2.972 pi. And for the right-hand integral, I'm getting 1.270 pi, giving me altogether 4.242 pi. This is a rounded answer. So at this point, if you want to plug that all into your calculator, 13.326 units cubed is my approximation of the area for that region. Okay, take a quick look. That is approximation by using the disk method, where I split it into 2 parts. And just as a summary, the region, I did split it into 2 regions, and I said everything above this line, all of these disks would be calculated using my parabola, which was the entire left-hand half here. And then the bottom half, all of these discs would be calculated using my right-hand integral there. So I did have to split it up. That's because my curve changed that was defining my radius of my disc that I was slicing. Hang on to that answer. We're going to do this, like I said, a second way, and I want to compare at the end, see if we actually do get the same answer, and I want you to think about which one is actually easier, okay? Before we go on, I want you to notice that my axis of rotation here is my vertical axis, my y-axis, line x equals 0, vertical line, and my slicing happened horizontally. I was slicing discs horizontally with respect to y. Okay, you could also say that your limit of integration and your dy matches with the axis that you're rotating around, the y-axis. Okay, I've got the same picture sketched here, same problem, so we're going to have to recall that our equation was y equals 4 minus x squared for the parabola, and then we had the line y equals x, just to remind us of that, and then of course the x-axis. And I'm still rotating it around the y-axis, not changing any of that. What I'm going to change this time is that instead of, so rotating around this axis, instead of slicing it horizontally, I'm actually going to slice it parallel to my axis of rotation. So I'm going to slice it vertically, just like my y-axis, with respect to the other variable. So it's going to look like this. I'm going to slice it vertically. I'm going to take a really, really thin slice, and I'm going to wrap it around. So it's actually going to make a cylinder, a cylindrical shell, if you can picture that. Well, I'm not going to talk about the thickness of that. I'm going to talk about the actual area of this tiny shell that I'm slicing out of here. Okay, and I'm going to essentially add up a whole bunch of those. If you can picture a whole bunch of shells that are all lined up right around that, and inside of that, each one very, very thin, the thickness of it represented by what we call dx, and I'm going to calculate the volume by adding up a whole bunch of those. So this is where I'm using my volume of a cylinder formula, 2 pi r times h, because I've got a cylindrical shell, and of course I'm using the integral to help me out, because it's going to add up a whole bunch of these. So I'm going to pull out my 2 pi, because those are my constants, and I need to define the radius and the height of this shell. So the radius is actually going to be, from the center out, is going to be my x value. That's really just my x. It's my x here, it's my x there. It doesn't matter where I am. It doesn't matter what curve I'm going to. It's my x, and I can actually use x before I had to solve for x in terms of y, because I was integrating with respect to y. But because I've already established that I'm going to be doing this with respect to x, I've got that right here, I can go ahead and say that my radius itself is just my variable x. That should look similar to one of the problems we did in class. Look at the one where we were revolving around the y-axis, and our radius was x. Now let's talk about our height. And our height of our cylinder is the distance from one curve to the other. Interesting. So I'm actually taking my y value of my upper curve, if you will, my parabola, but the y value of my parabola would have been, let's take a look at it here. The y value of the parabola would be all of this. So I'm taking that, but to get the height of my cylinder, which is just this green part, I'm actually having to subtract something off of it. And what I'm subtracting is really the distance, the y value of my other curve or my line. So that green height can be defined as the purple minus the orange, where the purple is really my height of my parabola. So that's my 4 minus x squared. And I'm subtracting from that the orange part, which is my height of my line. So that's giving me, in the end, that is giving me my height. And maybe we should do this. Maybe we should put parentheses around it. So I'm going to put an arrow, but I'm going to put parentheses because mathematically I have to multiply the height times the radius. Just take a second to make sure you can actually follow how I'm getting this as my height. Again, it's the purple, which was the entire length, minus the orange. So the purple was all of this to my x-axis, minus the orange was just this part, giving me my height. So I'm subtracting my two functions. Okay, we're all set up. So now we're going to integrate. Whoops, I forgot my limits of integration. I'm integrating with respect to x, so all I need to know is my x values. I'm going from 0 to the numerator, or the upper limit of integration is going to be that same value I had before, 1.562. So if we hadn't already done that, we would have to solve for that at this point. Recall that we found the point of intersection between my parabola and my linear function. Okay, let's go ahead and do this. So 2 pi times the integral from 0 to 1.562. I'm going to tidy things up a little bit. And it looks like I can go ahead and distribute. So I've got 4x minus x cubed minus x squared dx. And I'm going to now integrate. 2 pi times 4x squared over 2 minus x to the 4th over 4 minus x cubed over 3, integrating with respect to x from 0 to 1.562. I can simplify a little bit here, so I've got a 4 and 2, which can cancel. I've got 2x squared in the numerator. I think that's all I can do. So again, now would be a good time to grab your calculator. Go ahead and plug in the 1.562. For all of those x's, we're not actually going to have to do anything with the 0 because that's going to cancel out. So I've got 2 pi times 2.121 is what I got when I put in 1.562, equaling approximately 13.327 cubic units. Take a look at that answer, compare that to our first answer, and you should be noticing, yes, indeed, we did get the same answer. Now, my question to you, just for reflection, I know this video is getting long, but which way did you think was easier? This one might have been a little bit harder to set up, but I only had to do one integral, and I think our calculations were actually a lot easier once we got that one integral. So your choice, this one would work both ways, so there's not a better way to do it, but just two different options for you to now consider.